Finally, we're ready to look at section 4.5, which is where we see where we can use all of this stuff we've been learning about. Okay, so let's start with our compound interest formula. Now, compound interest is different than simple interest. Simple interest is where you just have an account or a debt that earns a certain amount of interest at a certain rate every year, and the interest is added in once a year. Compound interest is how most things are done, like credit cards or things like that, and that's where the interest, or yeah, even your savings accounts and things, where the interest is added in more than once per year. And so as a result, you actually end up earning interest on your interest and getting a little bit more than what the rate suggests. Okay, so our formula for compound interest is A equals P, so A for amount, P for principal, 1 plus R over N. So R is the rate as a percent, not as a percent, as a decimal. N is the number of times we compound in a year. N is the same thing here, the number of times it's compounded in a year. And T is the time in years. So this is N times T. So amount equals principal times 1 plus rate over number of compoundings, all to the number of compoundings times the number of years as our power. Okay, so all of those meanings in there are right there. Just a few things to remember when it tells you something is compounded a certain number of times. Like if we see the word quarterly, that would mean that n equals 4 because it happens 4 times a year. That's what quarterly means. Or if it's like semi-annually, I think that might have 2 n's. Semi-annually would be twice a year. Annually would be once a year. Monthly would be 12. Daily would be 365. Hourly would be 365 times 24. Anyway, we can increase the number of compoundings per year as requested or as desired for these problems. Okay, let's do example 1. Suppose $2,000 is invested in an account earning 3% annual interest compounded monthly. So n will equal 12 because it's compounded monthly, so 12 times per year. We're going to use our formula, how much will be in the account after 6 years. So A stands for the total amount with the principal plus the interest. So we're finding the total amount in the account after we invest $2,000. The 1 is so that you're doing your 100% of your investment. And then we have 0.03, but that's being done 12 times in the year, so we break that down into 12 pieces. And then that's going to be to the 12 times 6, because it's 12 times a year for 6 years. So this is going to be compounded 72 times. Okay, so then all we have to do is put this in a calculator, experiment with whatever calculator you're using to make sure that you're getting the right result with how you're putting it into your calculator, because that sometimes can be the biggest problem, is to make sure you're putting in enough parentheses, or to make sure you're changing your rate to a decimal. There's various ways to make mistakes and cause issues with your final answer. Okay, so after 6 years, the answer I'm getting is 23.93, and since this is money, I'm going to round it to the nearest cent, and my calculator says 0.896, so I'm going to round that to 90 cents, because 6 rounds my 89 up to 90. Okay, now we're going to use this to go backwards. How long will it take for the account to reach $35,000 or $3,500? So now we know the amount, and we're trying to find out how long that's going to take. So we've got the same information here, other than we do not know the number of years. And obviously, it's going to be quite a bit more than 6 years. Okay, so we've been learning how to solve stuff like this by using logarithms. The first thing we need to do is isolate. So step one, we're going to isolate our exponential. The exponential is the base with the exponent. So to do that, this 2,000 is in the way. We have this extra 2,000 times our base to the exponent. So we're going to go ahead and divide both sides by the 2,000, and that will get our exponential piece by itself. So 35 over 20, that reduces to 1.75. I'm just go ahead and kind of do things in decimals, I think would be fine. If you want, you can go ahead and combine this together. So 0.03 of 12 is 0.0025. So 1 plus that gives us 1.0025 as the base of our exponent. And then, of course, that's going to be to the 12t power. You don't have to simplify everything like that because sometimes the decimals are repeating, don't end, whatever. This turns out nice. So you could just leave this all as one piece that you keep plugging into your calculator when you need to. Okay, next we're going to take a log or a natural log of both sides. It doesn't matter which one we use. Natural log we always use when we have e because that helps things cancel out. So just for difference, I'm going to use log base 10, but it really doesn't matter as long as we follow our golden rule and do the same thing to both sides. So now we use our power property, which means we move that 12t to the front as a coefficient. This side of our problem hasn't changed. All right, we're getting closer. We've got the t in a place where we can get it by itself now. So to get the t by itself, we are going to divide by the 12 and divide by the log of 25 because all of those pieces are multiplying together. So we're just going to divide by the pieces we don't need. So divide by 12 log 25. How did my 1.0025 turn into 25? Uh-oh, I just realized I did that. Let's fix that really fast because some of you are probably going, wait, what happened? What did I miss? Yeah, I just made a mistake. That's all. So log of 1.0025 and same thing right here. I apologize for that. Apparently I didn't want to do as much writing as I needed to. 1.0025. And then this little piece, hopefully I can just move it. Oh, the whole thing is moving. So break that up, and then I can just grab this. All the technical difficulties, don't we love them? Huh. It's not gonna just let me grab it. Okay, let me see if I can do this, and this, and this, maybe. All right, Control G, did I get the whole thing? Nope, I knew I was missing a piece. There it is. All right, move that there. Now I've fixed my mistake. Would have been better if I had put that in correctly to begin with, but mistakes happen, right? So t is going to be equal to the log of 1.75 over 12 log 1.0025. Now it really does not make sense to leave this answer in this form, even though this is exact. We want to know a number of years to apply to this situation. So let's go ahead and type this in a calculator. Again, experiment with how to use your calculator correctly so that you can get the correct answer. Don't just trust me and think that your answer is correct. Actually type it in and try it and make sure that you know how to do this. Okay, so the use of parentheses is helpful. Doing pieces one at a time is helpful sometimes. So it looks like I've obtained the answer, 18.677. So we could approximate that to about 19 years to get to that high, or 19 years and maybe, or 18 years and like 8 months, which is 2/3 of a year.